Hi, my name is Rachel Trabert, and I've been testing TEM nanosieves this summer with atomic force microscopy and computer modeling. The application for this project is for the NanoFET program. It's an electric thruster that charges and sends particles through a sieve that's electrically static charged. So we want to make sure that when we charge these particles and apply a back pressure to them, that we don't rip the sieves. And also, we have to have a piezoelectric that vibrates to allow the particles to pass through the sieve. So we want to make sure that the piezoelectric doesn't cause any high stresses, because the sieve is a very thin membrane. It's only 100 nanometers thick. So these are my defined variables for the project: Young's modulus E, Poisson's ratio V, the distributed load Q. For the AFM, we actually model with a point load in the center, but for all the computer models, it's a distributed load across the membrane. H is the thickness of the sieve, which I said was 100 nanometers. L is the width of the sieve, which is it's like 0.5 millimeters, so 500 microns. And U is the deflection of the sieve when there's a load applied. The first order model that I've been working on, there's two models. The first order is made in MATLAB. It's based off of Timoshenko's theory of plates and shells, and this a specific case is for two edges of the plate clamped down, and the other two are free to move. The equation shown below is solved in the code for U. It's a guess and check. And it goes through, it finds the U that matches the left-hand side, and then it plugs it into all the equations for stress, moment, deflection, and what other values we are looking for. The program will return at the very end two tables for deflection with a perforation factor and one without the perforation factor, and two graphs, one for deflection versus the perforation factor, and one graph for the stress versus the perforation factor. The second model that I've been working on later this summer is FEM in Coventerware. This is actually taking the sieve, solid modeling it, and testing it there. So it'll be explained a little more in the following slides. Why are we doing two models? Why not just FEM? The models are predictive in nature. They help give us a configuration for NanoFET. So the FEM will also help us we can try different configurations of perforation or whatnot to see exactly what's the strongest sieve configuration. They're also really simple to use, but they're good for getting kind of close to the value that we're looking for when we're testing with the AFM. The FEM takes a lot of time to make and run, so to have a first order model is really nice because it only takes like 3 seconds to hit go on the program and get values out of it once you plug in what you need. And both models are useful in helping us refine what we need to do for NanoFET. And so this is an example of my first order model. Here's our table of values for figure 1. It gives you the moment, the maximum deflection in the center, two stresses, tensile stress and bending moment stress, and then max stress, which is the addition of the two previous stresses. The top box is for no perforation factor, and the bottom box is for our defined perforation factor, and that's just the area of the percentage of area that's left when you take the holes out. So the bottom graph is figure 2 is deflection versus the perforation factor. 1 is where you have a thin membrane at the very right that's just no holes, so a solid surface. And then as you move out towards the end, it's more of adding holes, but it's a percentage of it. So you go out and you can see that your deflection increases as you go towards 0. For stress, for figure 3, you can see that at 0 your stress is very low because there's no membrane there, and it gets higher as you go towards 1. This is what I'm modeling in Coventerware. This is an actual picture of a TEM sieve taken by an SEM. This is the sieve that we'll be planning on using. This one was actually made in-house, though, with micron-size holes. The sieves that we'll be using have nanometer-size holes. This is the sieve that we've started to make. Andy, the other person that I've been working with on this project, makes these in the NanoFab lab in the EECS building. So hopefully in future we'll have more of these to be able to test. This is my Coventerware model. You can't actually make it look like the actual picture because Coventerware has a hard time dealing with circles. So we modeled it, approximated it out to a square. Each edge is clamped down, so it's much more of an accurate analysis. And a distributed load is applied across the surface. The sieve is actually inside the beveled edge. You can hardly see it. It's very thin. Once again, it's just a layer over the silicon wafer pretty much. So our next step in this project is to really get some good data from AFM testing. These are our preliminary results here. You can see that the deflection curve here, it actually starts to yield because at the very top you can see the slope changing. So we hope to get more results. This is not for a sieve it's actually just for a thin membrane. So hopefully in the future we'll be able to have more data to compare with our technical theory. So thank you. This has been my research for the summer. I've really enjoyed working with SURE. It's been a great experience to stay here in Ann Arbor. And I've really liked working on this project. I've actually worked for the same group for the last 2 years on different projects and haven't actually been fortunate enough to stay here during the summer to actually work more closely with the teachers and grad students. So it's been a great experience.